Okay, we're now going to discuss the one last way of writing the Euler equation, that is writing them in streamlined coordinates, which yields a very useful way of thinking about how the streamlines and how the direction of the flow informs you on the pressure field. So we start from steady state Euler equation. So here we have then our flow, incompressible, and it's steady. So these now are really, what I'm representing are really streamlines. And so here, let's say you can consider this this streamline, and at every single point you can define a tangent vector and a normal vector. So what mathematicians can do is glue a coordinate system to that streamline, and S will be your coordinate along this direction, and N would be your coordinate along that direction, just like X would be your coordinate along the X direction and Y your coordinate along the Y direction. You can define a coordinate system locally, which would be called the streamline coordinates. And what mathematicians can do, which is much more differential geometry than what I know how to do or that you actually need, but is to rewrite these equations here in streamline coordinates. So this derivation is really far beyond what we can do, but I'll give you a few indications such that you can recognize some of the terms and where they're coming from. So think that in streamwise coordinates, your velocity vector u, right? If I'm assuming also the flow to be 2D. You can do it in 3D, but it's a bit more complicated, so let me just stick with 2D. Your velocity u, the first component is the component in the s direction, and the second component is the component in the n direction. So this is your first component, and the first component is really u, and it's a function of s and n, but here it's if I'm just following this streamline, the velocity is a function of s, and there is no velocity in the n direction because we are in streamline coordinates. Okay, and your gradient, think that the gradient has a partial in the s direction and a partial in the n direction. This is here your gradient. And another way of thinking about this is that u here really has just one component, us, along the tangent direction. And so if you rewrite the Euler equation in streamline coordinates, you can rewrite the Euler equation with one equation in the s direction, so this is along the tangent direction. The other equation will be rho times u s times partial u partial s. Note here that in streamwise coordinate, us is the velocity, so it's the magnitude of the velocity vector. Now this term here clearly looks like your inertial term, and this is really this term projected onto the streamwise direction, and that is going to be equal to minus partial ps, so the gradient along the s direction, minus partial phi partial s. So here maybe there is nothing too surprising. We'll discuss later on what this equation really represents, and then you have an equation along the normal direction, right? So if you project Euler equation in this direction, then what you have is that this term, the only remaining term of the u grad u term in the normal direction, is rho times the velocity squared, right? So the component in the s direction is really the velocity, divided by the radius of curvature of the streamline at point S, and I'll discuss this point in a bit, and that is equal to minus partial p partial n minus partial phi partial n. So those are our Euler equation in streamwise coordinate. Now let's discuss each of these equations, and let's start by the equation in the tangential direction. So you might already have a feeling for what this equation is. Now what I'm going to do is directly put those two terms on the left hand side. So I'll make that equal to 0 and change those minuses into pluses, and think that now we're projecting the equation along the tangent direction, but that we already did in just a few minutes ago, and you see it here again. So I can integrate this equation along the streamwise direction. Here you have a function times its derivative, so this is, when you integrate, this gives you the half of rho us squared, and when I integrate these two terms along the streamline direction, I get P plus our force potential. And here we had a 0, so when integrate we get a constant. So not surprisingly, Euler's equation in the tangential direction yields the Bernoulli equation. Okay, let's look at the normal direction. And so here I just want to do a brief reminder on the radius of curvature. So here assume this line is a streamline. This line here is a streamline. And so our tangent vector is of course always tangent to our streamline. Let's take a point at S and a point at S plus ds a little bit further along the streamline. The radius of curvature comes into play when we take the derivative of our tangent vector along the streamline. So dt ds. So dt ds is just this vector, the tangent vector at s plus ds minus the tangent vector at s, and we divide this by ds. Now the difference between this vector and that vector, you see this is a little, what has happened is that the tangent vector has turned a little bit. Now it's pointing a little bit upwards. So you see that when you take the difference, what you have is a vector in this direction, right? So it's a vector in the normal direction, and the flatter the curve is, the smaller this vector is, the difference is, and the more pronounced the curvature is, the bigger the difference is. So the difference between those two vectors is equal to normal vector times a quantity which is related to the curvature, which is 1 over the radius of curvature. Now note that if the tangent vector curves here upwards, so curves in this direction, then the radius of curvature is positive. But if it curves the other way around, then the radius of curvature is negative. Right, so if I have a streamline and the flow is in this direction, right, then tangent vector is in that direction, normal vector is in this direction, and here my radius of curvature is positive. But if I have the other orientation, so this is my streamline, tangent vector is here, normal vector is here, then in this case my radius of curvature is negative. So what do we learn from this equation? And to discuss that, let me assume that we neglect the effect of viscosity and we simply have the inertial term and the pressure term. Okay, so let's start with a simple streamline. So we assume this is our streamline. Right, what we learn is that here our radius of curvature is positive. Right, so this is positive, and therefore this has to be positive, and that means that partial p partial n is negative. So if you're at this point, your local streamline coordinate system is t and n, So partial P, partial N is negative along the N direction. That means that the pressure decreases along the N direction. So P decreases in this direction. And that makes sense, right? We've discussed that before. If P decreases, that means that P is larger here and is lower here. And that's what you need, because if you have a curvature, so if you're thinking about a material element here, right, the velocity vector of this material element is changing because it's not going into a straight line. And that means that the resultant force has to be non-zero, and the resultant force has to be pointing in this direction, which you can explain if, for instance, you have more pressure on that side of your material element and pressure on this side. So this is really consistent with your understanding and your knowledge of Newton's second law. Note also that the smaller the radius of curvature, the larger the pressure gradient. So if Rs is smaller, so if, for instance, instead of this curvature I have the same velocity, but now my streamline has a smaller radius of curvature, right? In that case, the radius of curvature is smaller. This is smaller, therefore this term is larger, and so my pressure gradient is larger. Okay, so if the more you have sharp radius, small radius of curvature, so more the curvature is large, the larger you can expect the pressure gradients to be. Okay, now conversely, if you have a streamline which goes the other direction, so if you have a streamline in this direction, right, then at any given point we can define our streamline coordinate system. And so in this case, you see here our radius of curvature is negative, while here it was positive. And so if our radius of curvature is negative, then this term is negative, because we have a minus sign here. dP dN is positive. And of course, this is consistent with what you already know from Newton's second law again. So that means that P increases along the N direction. So if P increases, that means that P is smaller here and larger here. And that is consistent with Newton's second law. If you had here a material element, right, this material element again, if you're looking at the resultant force, it is non-zero, because if the resultant force was zero, it would just continue straight along the t direction. And since the material element is being pushed along the streamline in this direction, that means that you have a net resultant force in the negative n. And that would correspond to a higher pressure here and a lower pressure here. So low pressure, high pressure, partial P, partial N, positive.